So I want to go over how to calculate molar mass. We've talked about molar mass of just individual elements, but we have to be able to calculate molar mass of entire compounds. So this is pretty simple. All you need is a calculator and a periodic table. So if I look at CO2, I find that there's 1 carbon and 2 oxygens. You just take the mass of 1 carbon from the periodic table, so that's 12.011, and you add it to the mass of 2 oxygens. So I'd multiply 2 times the mass of oxygen, 15.999. And so when I do that math, I get somewhere around 44.001, I think. And the unit of this is grams per mole. Double check that. I just don't have a calculator on me, so you'll want to double check that. That is how you find the molar mass of a full compound. Just take the subscripts, multiply it by the mass found on the periodic table, so the atomic masses, like here, and then add them up for each of the compounds. For percentage composition, what this allows us to do is to calculate what percentage of each individual element makes up a portion of the total mass. So the way you calculate percent comp is you just take part over whole, and then you multiply it by 100 to make it a percentage. So for CO2, the percentage of just carbon in CO2, the mass contribution of carbon was 12.011. So carbon puts in 12.011 grams to the total mass of the compound, which is that 44 number, and then I multiply it by 100 to turn it into percent, and then that's it. That's all you have to do to find percent composition. The next thing that we covered is just a little bit trickier. It's called empirical formula. I'm going to do number 7 because number 6 actually requires you to leave out one step. But first, let's define what an empirical formula is. An empirical formula, compared to what's called a molecular formula, is the reduced form of the subscripts. So all it shows you is the ratio that the atoms have to one another. So if a molecular formula is like C6H12O6, molecular formula tells me the exact number of atoms present in the compound. So in this compound there are 6 carbons, 12 hydrogens, 6 oxygens. But the empirical formula only tells me the ratio of those atoms to each other. So if I reduce all of these subscripts by a common factor, I could reduce these all by a factor of 6. And so the ratio of those atoms is 1 carbon for every 2 hydrogens for every 1 oxygen. So the molecular formula tells you the actual number of atoms. Empirical formula tells you only the ratio. So if I had something like H2O2, which is hydrogen peroxide, that's the molecular formula because there's 2 hydrogens and 2 oxygens, but the empirical formula is just HO because it's a 1-to-1 ratio. Or if I had just water, H2O, that's a 2-to-1 ratio, and you can't reduce that any further, so the empirical formula is still H2O. Okay, so that's by definition. Well, what if I wanted to calculate empirical formula given percent composition data? So there's like a little memory tool that you can use to remember how to do this, and I call it percent to mass, mass to moles, divide by smallest, and then multiply till whole. So there's basically 4 steps in calculating an empirical formula. So let's start with step 1, percent to mass. Percent to mass is really easy because if these numbers are given to us in percentages, then you literally just change the percent sign to a gram sign. So if I had 89.14 grams of AU and 10.80 grams of oxygen, that takes care of step 1. I've just changed the percent sign to a gram sign. Mass to moles. This is where we convert from grams of substance to moles of substance by dividing by the molar mass on the periodic table. So I look up to the periodic table, I find that gold has a molar mass of 196.967 grams for every 1 mole, and oxygen has a molar mass of 15.999 per 1 mole. So when I divide those out, I get some numbers. And at this step, you're going to want to carry your numbers out about 5 or 6 decimal places, because the more decimal places you carry out this data, the less trouble you're going to have later on. So we get 0.452563 moles of gold and 0.675042 moles of oxygen. So that's the mass to mole step. Next is divide by the smallest. So once you get to this phase, this is a ratio. So what this tells me is for every 0.452563 moles of gold, there is 0.675042 moles of oxygen in this particular compound. But I need to be able to represent these as whole numbers. So to do that, I divide by the smallest. So if I look at these two numbers, I pick whichever one is the smallest, which is this one, and I divide all of them by that value. So I divide all of them by this value. So when you divide a number by itself, you get 1. And then when I divide this by that number, I get pretty darn close to 1.5. So at this point, sometimes these numbers are whole numbers. They are already whole numbers. And if they are already whole numbers, then you're done. And you have to take a little bit of rounding liberties to determine whether you have some whole numbers. So if you have something that the decimal ends in like 0.97 or 0.1 or close to that, go ahead and round to the nearest whole number. But if it ends in something like 0.5 or 0.3 or 0.6, that's not quite close enough for us to round to the nearest whole number. So that's where step 4 comes in. We'll multiply till whole. So if it ends in 0.5, the thing you got to multiply by is 2 to get it to a whole number. If it ends in either 0.3 or 0.6, you can multiply by 3, and then you'll be close enough to a whole number. So since this ends in 0.5, I'm going to multiply by 2. But what you do to 1, you must do to everything, because we don't want to change the ratio. 1 to 1.5, if I multiply everything by 2, I end up with a 2 to 3 ratio, and that's the same as 1 to 1.5. So these numbers now are the numbers I'm going to use as my subscripts. So I got 2 moles of AU for every 3 moles of oxygen. That is my empirical formula. So there is my empirical formula. That's how you do that. Then what if you needed to go a step further to calculate a molecular formula? So to calculate a molecular formula, it's not that difficult. You have to know 2 things. You have to know the empirical formula, and you have to know the mass of the molecular formula. So if you're given the empirical formula, that's awesome. If you're not given the empirical formula, you're given this kind of stuff, well, that's enough to go through these steps to find the empirical formula, and then you can do the rest of the math. So here we know the empirical formula, and we know the molecular mass. So to find the molecular formula, all you have to do is take the molecular formula mass divide it by the empirical formula mass. When you do that, you're going to get a number. That number tells you what you have to multiply all your subscripts by. So the molecular formula mass is given to us. It's 180 divided by the empirical formula mass. So I find the mass of this, molar mass. So I got 12.011 grams from that one carbon. I got 2 hydrogens that are 1.008 grams apiece. And 1 oxygen at 15.999 grams. So I add all those things together, which I'm going to do real quick. And I get 30.026. So when I divide those out, 180 divided by 30 is almost exactly 6. And so now I just take that number and I multiply it by the subscripts. So this is C6H12O6. This document is in the Google Classroom, so grab it and finish working out the rest of the problems.
No.